everyone. My name is Micah, and I'm working at Software Mention in Membrane Framework project. And today's topic is WebRTC Redefined, a new SFU API from Membrane Framework. We are going to talk about WebRTC standard and its implementation in Elixir that we are working on in Membrane. The table of contents is as follows. First, we'll talk about what is Membrane. Next, we'll move to the what is WebRTC standard. In section 3, we'll talk about example usage of standard WebRTC API. And in section 4, we'll talk about problems of WebRTC. And finally, in section 5, we'll talk about Membrane WebRTC implementation, which we called RTC engine. So to begin with, what is Membrane Framework? Membrane Framework is a framework for processing multimedia. So whenever you want to do something with audio or video, you can try to use for it Membrane. I listed here some use cases. So for example, if you want to try to read audio or video file from audio or video file and play it, you can try to use for it Membrane. If you want to build your own video conference system and integrate it with your existing Phoenix application, you can try to use for this Membrane. The most basic and elementary entity in Membrane is an element. There are basically 4 types of elements in Membrane. Membrane elements are grouped and linked into pipelines. I would say that a pipeline is one directional flow of data. And here in this figure, I present a very simple membrane pipeline that is responsible for reading MP3 audio file and playing it in your headphones. So on the left side, we have MP3 file reader, and this element is of type source. So in Membrane, basically sources are used to read data from a file or from the network and pass this data to some other Membrane elements. Next, we have MP3 decoder, which is a filter. Filters in Membrane are elements that get data from other Membrane elements, modify this data, and pass this data to some other Membrane elements. In this case, MP3 decoder is responsible for decoding MP3 audio to raw audio. And next we have a converter, just because it's needed by port audio. And at the end we have a port audio, which is a sink. Sink is something opposite to the source. So it basically receives some data from other Membrane elements and saves this data to a file or sends through the network. There are also beans, but they are out of scope of this presentation. They are mostly used for logical purposes to group some Membrane elements. So this was a quick intro into Membrane Framework, and next we can move to the WebRTC standard. So WebRTC standard, first of all, it's a standard. It's not a protocol. It's a protocol umbrella. So WebRTC consists of many different multimedia and network protocols. And WebRTC standard enables peer-to-peer connections between browsers in scenarios when both peers are behind NATs. It is implemented by all major browsers, and WebRTC is basically consists of 2 planes, media plane and signaling plane. Media plane is responsible for carrying media and non-media data, so for example, audio and video or chat messages, while signaling plane is responsible for carrying messages that are related to negotiating session parameters. So for example, how many audio or video tracks are we gonna to send, or how many audio or video tracks we are able to receive, or which codecs we are able to use. Yes, and signaling plane in WebRTC is left to the user. This means that there exists functions in WebRTC API that you can use, that you have to use for creating signaling messages, but you have to carry these messages to your peer on your own. and you have to provide your own signaling server that you will send messages through. This figure presents a very simple scenario of peer-to-peer connection in WebRTC standards. So we have PCA and PCB. Both peers are behind NATs. And we have a signaling server. The basic question is here is how to establish a peer-to-peer connection when we have when both peers are behind NATs. So this is not shown in this figure, but we basically use one more server called stan server. And we ask this server for our public IP address. And when we send a request to a stan server, then we create a binding in our NAT table from private to public IP address, and then the stan server can reply to us with our public IP address. Both peers do the same, and then we exchange those public IP addresses through the signaling server, and we try to establish peer-to-peer connection. The whole process of fetching our public IP addresses, exchanging those addresses, and making a connection between two peers can be called or is included in so-called ICE protocol. So basically, our public IP addresses are also called ICE candidates. This is pretty important. And next we have WebRTC protocol stack. As I said, WebRTC is a protocol umbrella, so it basically consists of many different multimedia and network protocols. And here we have media plane and signaling plane. In media plane, the most important protocol is RTP. It carries media data like audio and video. And we use cryptographic context negotiated during the DTLS handshake to protect RTP packets. And this way we make from RTP packets SRTP packets. And there is also SCTP. There are also SCTP datagrams which are encapsulated into DTLS records. They are used for data channels, but this is also out of scope of this presentation. We have also ICE, STAN, and TERN. These protocols are for establishing peer-to-peer connection. And we, of course, have UDP IP stack. And in signaling plane, the most important protocol is SDP. SDP stands for Session Description Protocol. And a Session Description Protocol is a protocol that defines format of signaling messages. So whenever you want to say how many tracks we are able to receive or send, we have to construct a proper message called SDP offer, and the other side has to construct SDP answer. And SDP protocol defines how those messages should look like. This is a very simple example of SDP. SDP basically consists of so-called M-lines. Each M-line describes one audio or video track or data channel. And for example, here we have one audio that we will send. The direction is send only. And this audio can be encoded using 3 different codecs with number 111, 9, or 8. This is at the end of the first line. And then we have some mappings. We tell that codec 111 is Opus, while codec 8 is PCM-ALO. There are also some ICE and DTLS attributes or extension attributes and some identifiers and labels. I omitted them here because if I wanted to put it all here, it would take at least 2 slides. So basically, each M-line is pretty big. So, and when we have a conference for, let's say, 20 people, and we have, let's say, I don't know, 40 tracks, different tracks, this SDP offer answers becomes very complicated. I didn't say it, but WebRTC was intended for peer-to-peer scenarios, and then it was adapted to more complicated scenarios like video conference systems. And you can build video conference systems in 2 ways, basically, using SFU or MCU. SFU stands for Selective Forwarding Unit. It's just a server, and it is responsible for conveying media tracks from one peer to another peer. Let's assume that we have a scenario in which we have PCA and PCB. PCA transmits 2 tracks, and PCB transmits 1 track. We have also a PCC that is a passive participant. It will only receive audio. In case of SFU, PCC will receive 3 tracks, 2 from PCA and 1 from PCB. If we wanted to use MCU, then MCU would perform some multiplexing, some audio and video mixing, and yeah. So MCU basically requires some more computational resources to perform re-encoding. And now we will move to the example usage of standard WebRTC API. Because WebRTC API is natively implemented in all major browsers, we can use JavaScript to establish a peer-to-peer connection or to build our own video conference system. And now I will try to show you how to establish a peer-to-peer connection using the standard JavaScript API. So first of all, we have to create RTC peer connection. Here we pass ICE servers. Those ICE servers are IP addresses of basically stan servers or turn servers. And next we have to obtain our local stream from our local camera and microphone, and we need to add each track to the peer connection, which we are doing in a for loop. This is pretty straightforward, I think. There is nothing complicated. Next, we have to create SDP offer answer. So we have to tell our peer what we want to do, how many tracks we want to send, etc. So we basically create a SDP offer. Next, by calling create offer on peer connection. Next, we have to call set local description with this offer, and we have to send this offer through the signaling. We have to also be prepared for receiving SDP answer from our peer. So whenever we receive SDP answer, we set this on our peer connection. The problem with this code is that it requires from user some knowledge about SDP protocol. It also forces user to care about some race conditions, because 2 peers can send their offers at the same moment, and developer has to take care of this, which is not trivial. And next, we have to take care of ICE candidate. So we basically set on ICE candidate callback on peer connection, and whenever our peer connection will emit some ICE candidate, our public IP address, we have to transport this our public IP address to the other end. And to this end, we are calling signaling send with ICE candidate. And we have to also be prepared for receiving some remote ICE candidates. And whenever we receive some remote ICE candidate, we add this to our peer connection. So this code is pretty straightforward, but it requires from us knowledge about ICE protocol and ICE candidates. And this should work at this moment. We should receive new tracks in on-track callback, and we should be able to establish a connection. Next, let's assume that we want to add some tracks during the session. Let's assume that we want to add a screen sharing. So we obtain a new track, and we want to add this to our peer connection. We call peer connection add track with new track, but then we have to call also restart ICE, and we have to create a new offer, and we have to exchange once again offer and answer with other peer. So this becomes pretty complicated, because we have to know what is ICE restart, why we need to call this. We have to know when to call this, and we once again have to take care about some race conditions, because 2 peers can perform ICE restart at the same moment. And yeah. So what are problems of WebRTC? So the main problem is that user is forced to have a knowledge about SDP and ICE protocols. This is the first problem. The second problem is that changing session description parameters is pretty complicated. We have to take care of different race conditions. There is also no way to associate some metadata with tracks. The problem with this example is that when we added a new track, there is no way to distinct between different tracks of the same type. So when some other peer receives a second video track, it basically doesn't know whether it is a screen sharing or another video from some camera. User is forced to do this on its own using a signaling server and custom messages, and this is not trivial because of changing IDs in WebRTC standard. What is more, there is no abstraction layer. So if user want to implement abstraction like room or peer, it has to do this on its own, and it has to code all of this stuff on its own. Yeah, and here comes Membrane. We already implemented WebRTC in Elixir, but we also we also created some abstraction layer, and we called it RTC engine. So what is RTC engine? I would say that RTC engine is some kind of abstraction layer that allows you for creating video conference systems. Each instance of RTC engine, you can think about RTC engine as a room. Each instance of RTC engine can be a single video room. At this moment, there is only one type of engine called SFU, but we are also planning to introduce MCU. And we want to make RTC engine WebRTC agnostic. So our goal is to basically provide an abstraction layer and some callbacks with notifications, so that user or developer doesn't have to think about protocols or standards that are used under the hood. This figure presents architecture of Membrane RTC engine. We basically have a Membrane client library and Membrane RTC engine, and both of them emits so-called media events. Media events are responsible for carrying messages related to negotiating session parameters, or informing that there is a new peer or some peer left the room, or some metadata of some track has been updated. Those media events, the only thing that user is forced to do is to pass those media events to the other end. User doesn't have to know what types of media events there are, or what is the format of media events, or how to serialize media events. The only thing user has to do is to convey this from one side to the other side, and that's all. Whenever, let's say that we are in Membrane client library, whenever Membrane client library emits some media events, and this media event is passed to the Membrane RTC engine, Membrane RTC engine can emit some notification. For example, there is a new peer. Do you want to accept it? Or in opposite way, whenever Membrane RTC engine emits some media event and we pass this media event to Membrane client library, Membrane client library can call some callbacks, like on a new peer joined, or on peer left, or something like that. What's important here, we hide stuff related to SDP and ICE protocols in those media events, so that user doesn't have to know anything about this. We also solve all race conditions related to those things, so internally, so developer also doesn't have to think about any race conditions. And we was also important, we provide an abstraction layer with rooms and peers. Yeah, so now we'll talk about client-side API. The base class in our library is membrane WebRTC, and this class takes membrane WebRTC config. In config, we can specify some callbacks, RTC config, and receive media. RTC config is basically for passing stan servers. It's not mandatory, and the receive media is to say whether we want to receive media or only transmit media. Callbacks that we implemented at this moment are, of course, on send media event. Whenever our client library emits some media event, this callback will be invoked. So this callback basically has to carry data on the other side, to the other side. And media event is in serialized form, so this is basically binary form or string. There are also callbacks related to joining, like on join success or on join error. Those callbacks are called whenever a peer is accepted or denied by a server. There are also on track ready, track added, track removed, and track updated. Those callbacks are related to tracks. And for example, on track ready is called whenever some data related to a track arrives to the user. Or on track updated is called when some metadata has changed. And we have also three callbacks related to peers: on peer joined, on peer left, and on peer updated. Those are pretty similar to callbacks devoted to tracks. In functions, we have receive media event. This function should be called whenever we receive any media event through the signaling. And that's pretty it. And we have also join and leave. While joining, we can pass some metadata, and those metadata will be seen by other peers on peer joined. So here we have a callback on peer joined, and here we have a peer, and this metadata will be available in peer. So we can, for example, pass in join our display name. We have also update peer metadata function, add track, replace track, remove track, update track metadata. I think that they are pretty self-explaining. And now we'll move to the example usage of our client library. So we basically need to create membrane WebRTC class and pass and implement some callbacks. So we implement on send media event by sending something through the signaling server, and we are also implementing on track ready. In this callback, we can, for example, attach stream to a video HTML video element to display it in our browser. Next, we have on join success. So when we are accepted by a server, we can start adding our tracks. And you can see now how easy it is to add tracks and associate some metadata with them. Here we are adding 2 audios and 2 video tracks, and we are also associating some metadata to them. In this case, this is source, but this metadata can be anything. So we have source microphone and camera 1, and we group this into one stream, which means that audio and video will be synchronized. And we have also audio 2 and video 2, and the source of this tracks is from camera 2. So thanks to this, user can distinguish between tracks of the same type. We also specify on peer joined and on peer left callbacks. So whenever some peer joins or leaves, we can update, for example, our participant list. And we also, whenever we receive some media event on our signaling, we just pass this to our WebRTC instance. So after specifying this callback, we need to call WebRTC join. We pass here our display name. Yeah, and that's pretty it. So we don't have to think about any SDP or ICE stuff or race conditions, and we are provided with some abstraction layer. After some time, we can try to add more tracks. Let's say that we want to start the screen sharing. So we are just adding new video and audio tracks with source screen sharing, and that's all. I think that's pretty simple. And we have also server-side API. Server-side is pretty simple at this moment. Everything we need to do is to create a new instance of RTC engine and register ourselves for messages from RTC engine. That's all. Next, we have to be prepared for receiving media events from our RTC engine. This media event can be dedicated to all other peers. So the broadcast keyword is used, and we just send this media event to the signaling server process, and signaling server process will send this media event to all peers. Or media event can be dedicated to a specified peer, and we do the same. And next, we are also prepared for receiving media events from the network, and we just put this to our engine by sending this to engine. We can also receive two notifications. One notification is about new peer, and whenever a new peer appears, we can accept it or deny it. And we can also receive a notification about a notification peer left. So to sum up, a new membrane RTC engine API hides SDP and ICE stuff from the developer, provides you with peer and room abstraction layer, allows for easy media tracks manipulation. I think that's pretty important, and allows for associating metadata with tracks and peers. And what is, I think, the most important thing, RTC engine can be distributed across multiple machines. This is something that we are currently working on. It's not ready yet, but we managed to make some progress. The basic idea is to be able to run one room, so one RTC engine, across multiple machines. And thanks to this, we will enable very good scaling of our video conference systems, because Elixir is not as performant, not as fast as other languages like, let's see, Rust, Go, or C. But we can make some, or never mind. We can just be a little faster using our scaling methods and scaling abilities of Elixir. Yeah. Further work, at this moment, we are working on stability and performance improvements. I think that this is the most important thing. And we are also working on adding one more abstraction layer. This layer will allow you to modify RTC engine behavior. So you will basically be able to provide your own membrane elements, like filters or elements that will save your media tracks to a file. You will be able to plug such elements inside RTC engine. This is something that we are working on, planning, I think, and we are going to implement. And this will make our RTC engine very modular, I think, and very customizable. I mean, whenever you want to add some filter that will modify your audio or video, there wouldn't be any problem. It will be also possible to add some your own your custom endpoints, like endpoint for a SIP protocol that will enable you to phone connections, or an HLS endpoint that will save streams to HLS format. Yeah, so stuff like this. So I think that's pretty it. And yeah, that's all. Thank you for joining. I hope that you could learn something about Membrane and WebRTC stuff. Here are some useful links. We deployed our test version of WebRTC video room under the first link. I hope it should work, and you should be able to join there and try out our WebRTC video room based on our new RTC engine. And yeah, I think that's all.